Right, so we're now going to start gravitational potential energy. So far we have done the force between two objects due to gravity, and if I'm on a large mass, so let's say for instance the Earth, then the force that I'm pulled towards the Earth is called weight. And weight, as we know from the preliminary course, is mass times your gravitational acceleration. So that's the first thing we've done. Then we have a look at how to measure that with the pendulum. Now we move on to the amount of energy we have because we are in a gravitational field. So not just the pull down, the force, but energy. So the first thing we're going to look at is what is gravitational potential energy. And let's just do the formal definitions. Gravitational potential energy is the energy an object has just because it is in the middle of a gravitational field. This definition goes on, and it is important to understand the second part, which is just here. So it's not just the energy you have because you are in a gravitational field, but moreover, it is equal to a certain amount of work that needs to be done. And this work is the amount of work required to move the object from its current position to an infinite distance away, where there would be no gravitational field measurable from that object. Now, the second part is it's a definition of idealism. It can't be done, it's not possible. But we use it very much in our understanding of escape velocity and orbital velocities. Okay. In a few more moments, after I've done my description, I'm going to give you some time to answer, help with the person beside you, question 2. So to do question 2, you need to now listen to me and try and work out what's going on. Now, just having a look at this box, I'm holding a box for people at home. If I was to put it here, I'm holding for people at home, it's at waist height. Would I, if I let it go, what would it do? Fall. Falling is a natural movement, isn't it? Yeah. Okay. If I was to move it from waist height to around about shoulder height or higher, is it a natural movement? No. Now, I'm talking about natural movements. Where have we met natural movements in a field before? Sorry? Right. Electrical particles in an electrical field. Charged particles in an electrical field. If an object moves naturally in a field, it loses the type of energy that it's got at the moment, the potential energy. So here, as this box drops, it will start to lose gravitational potential energy. It's a natural movement. And it converts that into something else. Remember, potential energy becomes real, not becomes a real energy, but other form of energy as the natural movement occurs. So once again, here's the box. It is now naturally moving towards the centre. It's going to convert gravitational potential energy into kinetic energy. Good. Going back. Going from here to here. In other words, I'm raising it against the field. It's unnatural. What must be done for this to occur? Sorry, no, it's a W word. Work. Work must be done. In other words, something, some external agent, in this case it's my arm, must put extra energy into the system. And when this happens, it increases the potential energy. So looking over here, make sure you understand this. At this point here, which is at shoulder height, if I let go, it loses gravitational potential energy. It gets less. If I push it the other way, what must it do? Gain. It must gain. Okay? And that gain comes from doing something. In this case, it's coming from my shoulder, and that energy that my shoulder used to make it rise is chemical energy from my food. Is that clear? Right. Now, again, the diagram that you have in front of you, I'm just going to skip to that one for a few seconds. Yeah. The diagram you have in front of you is that's the planet. This is the surface of the planet. And there is an object, we'll just put an object just here. Okay? Now, I want you to put that dot right in the middle of that line. You can see it there. Okay? If I move the object this direction, if the object moves naturally that way, what will it do? It will lose or gain gravitational potential energy. Right, it loses potential energy, gravitational potential energy. Now, the symbol for potential energy, no matter what, is this symbol, E with a little p down the bottom. That's the same symbol we use for gravitational potential energy, as electrical potential energy, as any other potential energy. So it loses that way. If it moves this way, what must it do? It must gain potential energy. In this case, because it's in a gravitational field, what's the type of potential energy it will gain? Gravitational potential energy. Okay. Now, let's go back to the natural movement. Remember, a natural movement does not need to have any agent for this to occur. It just needs release. As it moves from here to here, it will lose gravitational potential energy. And what will it naturally gain as a result? It gains kinetic energy. Okay? This is a natural movement. Natural movements are natural because there is work being done, but this work is being done by the actual planet's gravity. Okay? The reason why it moves towards the planet is the gravitational field. So natural movements are done, so I won't say are done, I'll say the work is done by the gravitational field. So, the planet's gravitational field causes natural movement, and natural movement means it is drawn towards it, and if you draw an object towards it, it loses gravitational potential energy, and it must gain kinetic energy. Okay, now let's do the unnatural movement. Next one, come up. Now, if natural movements are done by the field, the big gravitational field of that planet, then unnatural movements are done by an external agent. And this is work done by an external agent. Okay? Now, we can't say that it's going to, all we can say is it's going to gain we're going to gain potential energy, gravitational potential energy. We can't say it loses kinetic energy because it was stationary to begin with, like my box. Is my box stationary? How much kinetic energy has it got now? Nothing, has it? And if I move it up to here, how much kinetic energy has it got now? Nothing. But it had kinetic energy only during its transition. So unlike the natural movement, which is a pair of things happening, this is just simply a gain of potential energy, but we can now tell us where this gain comes from. From energy of agent. The external agent has to put this energy into it. Okay? And in my case, when I was raising it, was my arms, it was muscle. The muscle uses chemical energy. Okay? If this is a rocket, because we have to put everything back to being a rocket, okay, A rocket can simply fall towards the Earth and plummet to its doom. If it does that, what object is doing the work? It's the planet. The gravitational field of the planet does the work. However, we don't want doom to happen. We want the rocket to go this direction. So what do I fire at the back of the rocket? Rockets, yeah. Engines. The engines push it away from the planet. So this is the external agent. It's the engines. What type of energy transformation is going on here? It's chemical energy, isn't it? Chemical energy gets burnt and created into hot gas, which is spewed out the back. So most of the time, the movement across here is a transformation from the chemical energy. There is no hand of God pushing this away. So there's no massive hand like mine pushing it up into space. Okay? I know I shouldn't say I'm God, but anyway. Right here, is that making sense? And we have already done all of this with the electrical charge. So it's identical there. Okay? So can you see that the diagram, I haven't finished the diagram yet. That's the basis of the diagram you see on page 7. Okay? Now, that's the basis. Now I have to do something which is going to be really, really hard for you to understand. And it's always hard for all physicists. I hated it as well. And it's this. We have to make the mathematics work. Maths is the queen of physics. If the mathematics doesn't match, then physics has to bow to the mathematics. And so when we do this, we have to make sure that all of physics works. When we talk about energy, we don't normally have any sign to it. We don't have any positive energy. There's no such thing as negative energy. Okay? If I just say how much energy has something got, you say 15 joules. But that doesn't work for gravitational potential energy. Gravitational potential energy has to be a negative value. Okay? It's energy that is directed down towards. Okay? So I'm not going to explain anything more than you have to just accept that for the mathematics to work, that we have to have gravitational potential energy as a negative value, negative energy. Okay? And gravitational potential energy starts from, here's a planet down the bottom there, that's Earth, if you don't recognise it. And as this thing moves from here and out, it gets further and further away from the planet. Okay? Rightio. So, I'm just going to put it just there. Everyone happy with where I put it? Want to see that? Okay. I'm now going to move it here. What will it do? I've moved it towards the planet. Will it gain or lose gravitational potential energy? Lose. So, it has a certain value here, and I'll just put a big capital X here. And as it's going over here, it's got less X. Is that right? If I move it further away to here, has it gained more gravitational potential energy? Yes. So when I come to here, I've got a large amount of gravitational potential energy. Is that clear? Okay. So this is the problem that maths puts up. The further and further I go away from the planet, actually, before I go here, I'll go back to where I've got, everyone happy that that's a little x? That just means I've got a small amount of gravitational potential energy. Is that clear? If I let it go, what's going to happen now? It's going to fall back to the planet. Isn't that right? Okay. So therefore, and as it falls, what's going to create? Kinetic energy. Good. Now I move to here. I let it go again. It's further away. What can you tell me about the gravitational field? It's weaker, isn't it? Therefore, the pull that's going to pull it back down is weaker. So will it still fall back to the planet? Yes. Yes. Okay. So it will start to gain kinetic energy. Will that gain of kinetic energy be very quick? No, because it's not being pulled by the planet anymore as much. Now I take it really farther away. It's got a large amount of gravitational potential energy, is that right? Yeah. What's the gravitational field like out there? Right, so if I let it go, will it rapidly come towards the Earth? No, it will just slowly, over a long time start to fall and get faster and faster. It might take years for it to fall back down to Earth. Okay? So therefore, over here, it's got a large gravitational potential energy, but it's not got a lot of ability to change it into kinetic energy, is it? As I move further and further away, let's now put it all the way over here, nearly infinite distance away. What's the gravitational field all the way out here, out there, so far away from the Earth? 0. If it's got 0 gravitational field out there from the Earth, will it fall back to the Earth? No. So it will never transform energy back into kinetic energy. So what's the only shape that will graph this? And here it is. It's an inverse hyperbola. As we go further and further away, you gain gravitational potential energy. Are we okay with that? So this red dot goes up towards the 0. Okay? But as it gets further and further away, what's happening? It's getting less and less able to convert that energy back into kinetic energy. Are we okay with that? So the only mathematics that works is this. So it must be negative, okay? And it comes down to there. At that point, where am I? Right, I'm on the surface of the Earth. So the lowest possible value of the gravitational potential energy occurs on the surface of the Earth, or surface of the planet. Okay? It can't go any further in because you'll be in the soil. Are we okay with that? Right, yeah. Now, I hope you've got that. If not, let's just take 5 seconds to work this out. Okay, remember, here's my rock. If it's natural movement, what will it do? It will, right, it'll go that direction. It will lose or gain gravitational potential energy? Lose. Now remember, gravitational potential energy is already negative, so it becomes more negative. Okay? Okay. So as it falls naturally towards the centre, EP is translated into kinetic energy. So EP is transformed into kinetic energy. But we already know that. Okay. If I was to project the object, in other words, I throw it from the surface of the Earth really fast straight up, okay, what will it do? It will move from here up, and eventually it will slow to a halt and then come back, getting faster and faster. Is that right? Okay. So as I throw it up, what's it going to do? It's going to translate that energy that it gains into gravitational potential, and then it's going to lose it coming back down. Are we okay with that? This is the one where we fire a rocket out and it's not going to come back. Why?
It's
right, it's got chemical energy and it's a rocket, it's engines, both of you are right, and that's the external agent increasing its gravitational potential energy towards 0. Okay? Yeah. So, the maximum kinetic potential energy you can have is 0. Okay? Right here. So, here is this diagram that you are going to take a few moments to write. All of this information that you see here must be somehow incorporated in those lines. Okay? So, don't forget, you might want to draw this diagram here. This is the This is the gravitational potential energy. I'm going to give you the formula in a few moments because there is a formula that describes this graph. But there is a vertical asymptote here, and that vertical asymptote is at 1 radius. We measure gravitational potential energy from 1 radius on the surface. It is most negative, it is least, most negative, everyone happy about those two terms, on the surface of the planet. It rises at its maximum value, and as it gets further and further and further away, the curve asymptotes horizontally to 0. So it becomes more and more 0. Okay? It will become 0 only at one point, an infinite distance away. Obviously, we can't be an infinite distance away, so it's a theoretical value only. Please realise that as that red ball goes up, that means there is an increase. As it comes back down towards the planet, there is a decrease. Okay? Are we okay with that? The formula for it, it's on the next slide, but I will just put it onto this one here. Sorry? Oh, it's on the top of the page. Good. Okay. It's minus G mm on R, and I'm going to derive that for you in a tick. The negative here is simply because it has to be mathematically sustainable in this understanding. And what do you recognise this as? Does it look familiar to you?
Yeah.
Yes, the GMM. Normally it's over what? R squared. Good. That would make it a force. So F and G are somehow related to each other. Okay? Sorry, not G, that's not G, that's meant to be EP. So there's a relationship between them. And I'm going to describe that in a few moments, but I don't want to cloud the water here. Okay, can you take now about 5 minutes to fill in that large section down the bottom of page 7, which is question 2. There is a little call out to the side, which has a little checklist of all the things that you definitely need to incorporate in your response. Let's now use this equation here. This is the equation. Now, just all you've got to remember is the negative sign here has come from our understanding of mathematics to make the whole idea that as you move away from a planet, you have to gain gravitational, but at an infinite distance, it must be 0. There's only one way that can happen. So where does the rest of the formula come from? Well, we know that work and energy are the same thing. And we know that work is force times distance. Okay? Now, the force of gravity in this case, if that's the force of gravity, would be Gmm on R squared. And if we multiply it by R, we get Gmm on R. And by putting the minus sign, it makes the mathematics work. So that's how this formula is derived. It's simply from what we already know as work. And that's the formula that we're using all through this preliminary year. Now it's in the HSC year. Okay? So all we now need to do is apply it, and you can see that the gravitational potential energy is just dependent upon 2 things, or 3 things actually. The 2 masses, the mass of the planet, M, and the mass of the rocket or the object that's in the gravitational. And then the last part is the distance that this is away. Oops. The distance that this is away is R. So this distance from the centre, from the centre out to here is R. Okay? Are we okay with all this? So, resetting that. We're going to calculate the gravitational potential energy of this rocket. Now it's got a mass of 2,000 kilograms, and we're going to put it on the surface of the Earth. So we need to know the mass of the Earth, and we need to know the radius of the Earth. All of these radiuses should be given to you in kilometres or metres. That's basically it. So if it is in kilometres, please don't forget you must convert it to metres. Okay? So, shoving in the numbers, you get EP is equal to negative 6.67 by 10 to the minus 11 times the mass of the Earth, which is 5.98 times 10 to the 24, times the other mass, which is 2,000, all divided by the radius, which is 64,000, and then add another 1,000 because of that. Okay? Now, the energy that an object has, because the Earth is massive, the gravitational potential energy will be massive. They're in megajoules. How many joules is that?
Maybe 1.25 times 10 to the 11.
By 10 to the 11th joules. Good. Okay? So that's it. That's megajoules, yeah?
How can you convert 2,000 kilograms to meters?
Oh, no.
It's kilograms. You can't convert to meters.
Yeah.
Sweet. Okay, rightio. Are we okay with that? The next one here says if I was to move it to 2,000 kilometres away, you would just do it again. Okay? Can I get you on the worksheet 1C to fill in the top three questions? We're not going to do this question here, but just so that you can work this out. This one here is a rocket moves to an altitude. So it moves out to here, which is 20,000 kilometres. The radius, this R here, is the distance between the rocket and the centre of the Earth. So when they say altitude, you have to work out the 20,000 here plus the 6,400 kilometres for the radius.
So this is different for the center of the other object or just
The centre of the other object and the other object will be the same. Okay, so that's always assumed. You don't need to worry about the centre of the small object. Okay. Right, you are. Is that making sense what I was just talking about there?
So you have to take the radius of the Earth plus the altitude.
Yeah, this is because this says an altitude.
And if it says radius,
If it says radius, the radius between them, you just use the R. Okay? So that's just, you'll be practicing a few of those in a few seconds. Okay, now, this is the one that's in your book, not this is directly in your book, but just getting the whole idea. I want you to, this is not, it looks like the Earth, but it's a pretend Earth, okay? I've written along here what are the potentials at a certain point. So if an object is here, it's, because of its position, it's 5 megajoules. Because the distance that it is away from the centre, there's the radius. Okay? So that radius and the mass of that blue dot and the mass of the Earth and doing all the calculation gives you -5 megajoules. Are you okay with that? Now, if I was to take this and move it to there, it's on a concentric circle. It's on a circle. Okay? Has it moved any further away from the centre of the planet? No. Has it moved towards the planet? So what can you tell me is the gravitational potential energy here? It's -5, isn't it? Okay? What happens, how much energy is needed for that to happen? For it to move from there to there? What's needed? See that? Is it getting any closer or getting further away? No. So, is there any energy needed for it to stay in a circular path above the Earth at the same height? No. This we call an orbit. That requires no energy. It will do it forever and ever Amen. Okay? So, as long as it stays in a certain place, in a certain distance above the surface of the earth, come on, rotate, and it keeps on doing it over and over and over again, it will do that without need for any input of energy ever. No work required. Because it's not changing energy. There is no energy. It will stay in that orbit forever. That's the reason why we're in the same orbit that we are going around the Earth, around the Sun. We don't need any energy to keep us going. Once started, there's no friction up there. So once started, the motion will just go on forever. Okay? It's like throwing a tennis ball in space where there's no gravity. Right? Just to throw a tennis ball, just off it goes. It will continue on forever according to Newton's first law. Okay? The only way it will change direction, it has to get a force.
So then why doesn't it just like drift us straight? Is it because the gravity?
Because gravity constantly bends it in. Now we're going to, when we do orbits, it'll make more sense. But okay, now, how much energy has that one got?
The same.
No, going around. Oh yes, it is. That one there has got 10. Okay. Now, how much energy is needed to move it? That's minus 10 there. Out to say there. I'm going to move it from here to there. Okay. Now, if I move it from here to here, how much energy is needed? That's minus 10, this would be minus 5. So how much energy is needed? 5. Okay? Now, how do I calculate that? The amount of energy needed, the amount of work is delta E, and it's final minus initial. Okay? Right, what's the final position? It's minus 5, isn't it? Minus, what was its initial? Negative 10. So 5 minus minus 10 equals 5 megajoules. 5 megajoules of work is needed to move it from here, that's this point, up to that point. Now remember, how much energy is needed to move it from here to here? None. No energy is needed. So how much energy is needed to move it along this round path? Only 5 still, isn't it? How much energy is needed just to move it along the red straight line? 5. Doesn't matter what path I take, it will just be 5. So that's 5. That's 5. All of them are 5 because it's just final minus initial. Okay? Rightio. So on your diagram there, you have a look at the one that you're in your book. At point A is in orbit. There's the orbit of A. Up there. That point there the object has minus 25 megajoules of energy. Okay? Point B is over here. It's in a circular orbit. That means it's not getting further away from the centre of the planet or so on. So what's the gravitational potential energy here? Minus 25. Why? Good. It's in an orbit, but more importantly, you can justify it by minus G M on R. What has not changed?
Radius.
R does not change. Yep, that's R. That's a radius. That's the radius between centre here and out. Right. Now, state the amount of energy to move it from A to a point out here, which is C, and that's minus 10 megajoules. Sorry?
Doing 80.
I'm doing C.
Already done.
I've done it. Okay, so I'm going to move it from there to there. Okay? How much energy is needed for that to happen? How much work is that, by the way, would that be a natural motion? No. So an external agent, most likely a rocket, is needed. Will it be a straight path? We don't know, but let's pretend it is a straight path. That's its final. Its final is, so delta EP, the change is final minus initial. So it equals -10 minus -25. So it equals 15 megajoules. So we need to fire our rockets and expend 15 megajoules of chemical energy. Is that making sense? Okay. Identify a possible source. What was it? Chemicals, rocket fuel. Excellent. Rightio. I want you now to try question number 2, please, on the sheet.